Let's jump right into today's explainer. We're exploring how our brains dynamically adapt to a constantly changing landscape, and we're tackling this from two totally different angles. First, the internal chemistry flowing through our bodies, and second, the external sensory world we navigate every single day. So let's just dive right in.
So, I want you to keep this guiding question in mind. How does your brain handle a changing world, both inside and out? Because the reality is, your brain is literally never truly at rest. It's constantly adjusting, remodeling, and reacting just to keep you functioning. Whether it's a shift in your internal hormones or, a sudden overwhelming noise in your environment, your brain has this biological reality of adaptability that is just absolutely incredible.
Here's our quick roadmap for this explainer. 1. Our dynamic adapting brains. 2. Estrogen reshapes brain connections. 3. Tracking menopause and memory. 4. Understanding unique sensory quirks. 5. The science of stimming. And finally 6. Helping with sensory overload.
Section 1. Our dynamic adapting brains. We really have to fundamentally change how we think about the human brain. It is definitely not a rigid computer hard drive. It's a living, breathing, and highly adaptable structure. The brain dynamically reshapes its connections in response to internal chemical fluctuations and external environments. This dual capability, reacting to microscopic hormones on the inside and loud physical stimuli on the outside, is what makes neurology so absolutely fascinating. Your brain literally changes its physical mechanical properties based on what it's exposed to, and researchers are just now figuring out how to actually measure these changes in real time.
Section 2. Estrogen reshapes brain connections.
That brings us to a groundbreaking new study out of the University of Delaware regarding estrogen and memory, which completely reframes how we view hormonal fluctuations. The technology making this discovery possible is called magnetic resonance elastography, or MRA for short. Think of it as an imaging technique that doesn't just take a static, boring picture, but actually measures the mechanical stiffness and elasticity of brain tissues. The researchers focus this on the hippocampus, which, as you know, is the brain region heavily involved in memory and learning. Through MRE, they could physically detect mechanical changes in this exact area across the reproductive cycle. Katrina Milbacher, a postdoctoral researcher involved in the study, put it perfectly. She noted, across the reproductive cycle, the brain adapts, relying more heavily on different regions at different times. The crucial point here is that estrogen fluctuations aren't just mood shifters, right? They actively influence the brain to reshape connections between neurons. It's wild. The brain's mechanical properties actually change depending on estrogen levels.
Section 3. Tracking menopause and memory.
So if the brain relies on estrogen to dynamically reshape its connections during a standard reproductive cycle, what happens during major hormonal transitions like menopause? Well, we've got a striking contrast here. During a standard cycle, the hippocampus undergoes dynamic mechanical adaptations. But during menopause, a life stage where the body obviously produces much lower levels of estrogen, researchers suspect the brain enters a mechanical stuck state. This is a profoundly different way to understand cognitive disruptions. We aren't just talking about vague symptoms anymore. We're looking at a suspected physical mechanical reality in the brain's learning center due to depleted estrogen. Associate Professor Curtis Johnson explains this so well. He says, "We suspect there may be a mechanical stuck state when estrogen is first depleted, contributing to disrupted cognitive function like brain fog." I mean, this is incredibly validating for anyone who's ever experienced brain fog during menopause. Imaging is so often just viewed as a tool for detecting disease, but as this study totally shows, it can also help us understand brain health dynamically across different life stages. And honestly, here's the most exciting clinical application of this research: 1 minute. The team at the University of Delaware is working hard to translate these findings from animal models to humans. Their ultimate goal is to make MRI imaging fast enough that it can be thrown into routine MRI exams, adding literally less than a single minute to a standard scan. That tiny 1-minute addition could allow doctors to track dynamic brain health and really support individuals through years-long transitions like menopause. How cool is that? Section 4. Understanding unique sensory quirks. Okay, so we've seen how the brain adapts mechanically to its internal hormonal environment. Now, let's pivot to the external environment and shift our focus directly to sensory quirks. To understand this, we need to look at individuals who are 2E, or twice exceptional. These are individuals whose brains just process sensory inputs differently than most people. Their unique sensory quirks mean they often experience the world much, much more intensely. Because of this, their dynamic brains can either get easily overwhelmed by their surroundings, or, on the flip side, they might actually crave extrasensory inputs just to feel balanced. Let's break down the extreme contrast of what these sensory differences actually look like in reality. On one end, you have super sensitive or over-responsive brains. To them, normal everyday sounds like a ticking clock or a dripping faucet, those can feel as aggressively loud as a roaring chainsaw. A tag on their clothing might literally feel like rough sandpaper scraping their skin all day. But then on the other end of the spectrum, you have undersensitive or under-responsive brains. These individuals might not even feel pain or cold normally. They might constantly bump into things simply because their brain doesn't naturally register where their body is in space. It's a wildly different way of experiencing the exact same external reality.
Section 5. The science of simming.
So, if your brain is constantly overwhelmed or maybe totally understimulated by the environment, what do? Well, you adapt. Sensory-seeking satisfaction is a massive part of this biological puzzle. A 2E person might exhibit behaviors like moving constantly, tapping objects, humming, or knocking on surfaces. Now, to an outside observer, someone knocking on a desk over and over might just seem completely random, but neurologically, it is entirely purposeful. They're seeking out specific inputs to achieve that sensory satisfaction. Maybe that physical vibration or the repetitive sound just feels deeply grounding to their brain. We call this stimming, which is short for self-stimulatory behavior. And the absolutely crucial point here is that stimming is a completely natural way for a neurodivergent brain to calm down, to focus, or to cope with a stressful environment. It's not a distraction, guys. It is a biological coping mechanism. Just like the hippocampus relies on estrogen to function optimally, a 2E brain relies on these self-stimulatory behaviors to regulate its sensory processing.
Section 6. Helping with sensory overload.
So, how do we apply this science? If you're a teacher in a classroom or a parent of a 2E child at home, understanding this entirely changes how you help them navigate their sensory quirks and deal with sensory overload. Here is a super logical 3-step progression to help. Step 1, recognize stimming for exactly what it is, a natural coping mechanism. If a kid is humming or tapping, realize their brain is actively trying to regulate itself. Step 2, identify the trigger. Look at the environment around them. Is there a buzzing fluorescent light, a ticking clock, maybe a scratchy uniform? You've got to identify the sights, sounds, or touches that might feel like a chainsaw or sandpaper to them. And step 3, intervene to reduce that sensory overload. Once you actually know their brain processes the world this intensely, you can provide the right support, whether that means removing the noisy trigger entirely, allowing them to safely seek out the physical vibrations they're craving, or honestly, just giving them a quiet space to regulate. We've covered some truly incredible ground in this explainer today. From the way estrogen dynamically reshapes the mechanical connections of our memory centers, all the way to how twice-exceptional brains utilize stimming to navigate a super intense sensory world. The human brain is just an absolute master of adaptation. So I'll leave you with this final provocative thought to reflect on. Knowing how dynamically your brain adopts, what sensory inputs or internal shifts are shaping your reality today? Thanks for hanging out and being such focused learners, and I really encourage you to keep exploring the amazing science of your own inside-out brain.